Alright, we're still talking about the behavior of rational functions, and let's pull up that screen we were just looking at with this function, x to the fourth minus 4x squared plus 1 over x squared minus 1. And we did all this long division, which is a tedious, cumbersome process, but it gave us this result, that the function behaved like a parabola for large values of x. Well, it turns out we typically don't have to do that. If all we need to know is the end behavior of the function, and we don't need to know the actual slant or curved asymptote, and we don't need an actual graph, if all we need is the end behavior, then there's a really nice shortcut that we can use that can avoid all of this work right here. So let's erase that. Take a look at this function and imagine x getting really big, and look first at the numerator and realize that as x gets big, x to the fourth is going to get bigger much faster than these lower power terms, so these lower power terms become insignificant by comparison. Apply the same reasoning to the denominator. The highest power term in the denominator dominates all of the others. The others become insignificant by comparison as x gets really big. So as x approaches infinity, or in other words, as x gets really large, the lower power terms become insignificant, and this function will behave like what you see remaining here after those other terms have been ignored. It will behave like x to the fourth over x squared. And that's really easy. X to the fourth over x squared simplifies to x squared. And we know what x squared looks like. We know that's a parabola opening up. And if you just know that graph, x squared, has a shape something like this, then you can see as x becomes big, the value of the function gets really huge, and as x becomes extreme in the negative direction, the value of the function becomes really huge. And you can go straight to this. The limit as x approaches positive infinity of f of x is positive infinity in this case, and the limit as x approaches negative infinity of f of x is also, in this case, positive infinity. And you can get that just by looking at the lead terms, because the lower power terms become insignificant. And that thought process can be really fast and efficient and useful, especially if you have a really difficult function to work with, like this next example. Here we have f of x is equal to 2x to the fourth plus 37x cubed minus 4,285.3 x squared plus 2.8 over pi squared x minus 721.9 over x minus 0.00328. Now, I don't think any of us want to start doing the polynomial long division with this. These numbers will get really messy. We have an irrational number up here in our coefficients, these decimal places that are going to make things more complicated. If we just want to know the end behavior of the function, if we just want to know what happens to the function as x becomes really big, and what happens to the function as x becomes really small, or really big in the negative direction. If all we need to know is the end behavior, what happens way to the left and way to the right, then we just have to look at the higher power terms. As x becomes huge, all of these lower power terms become insignificant compared to that x to the fourth term. And this certainly becomes insignificant compared to x. So as x becomes huge, f of x will behave, it will be approximately equal to 2x to the fourth over x. And that's real simple. That simplifies to 2x cubed. So as x becomes large, this function behaves like 2x cubed. And 2x cubed you should recognize is a cubic function that is going to look something like that. This little function definition right here should conjure up in your mind this mental picture, and you should be able to see from this, even if you don't sketch it, you should be able to see mentally that as x grows really large, this function zooms up, and as x grows to extreme numbers in the negative direction, this function zooms down. So we can say the limit as x approaches infinity, in this case, is positive infinity, And the limit as x approaches negative infinity, in this case, is negative infinity. And that's our answer. And that is far superior to doing all of the polynomial long division. To do this, you just have to remember the end behavior for polynomial functions, and then the end behavior from all the rational functions follows from that. So let's just review real quick the end behavior of polynomial functions. If we have an equation of degree 2, for example, so this would be some kind of parabola, ax squared plus bx plus c, where a, b, and c can be any numbers, then it is going to look something like this. Okay, it may be above or below the axis, but we know that it's going to be going up as x values get really big, and over here on the left we know it's going to be going up for a parabola every single time. If it's degree 3, a cubic, and a cubic would be ax cubed plus bx squared, and so on. We could have other terms, but we know a cubic typically is going to look like this. As x values become large, the function goes up, and as x values go to extremely negative numbers, the function goes down. And you see a pattern here for a degree 4 equation, which would be ax to the 4th plus bx cubed, and so on. A 4th degree function will look something like this. And exactly how it behaves here in the middle, which is often the interesting part of the function, exactly how it behaves there depends on these coefficients and whether they're positive or negative. But one thing we do know, if we're only interested in the end behavior, is as x becomes big, a 4th power function goes up, and as x becomes big in the negative direction, the 4th power function again goes up. For degree 5, which would be ax to the 5th, and so on, a 5th degree function will have some kind of shape like this. Let me try that again. And it may or may not wobble noticeably in here, but we do know that if it's a degree 5 function, as x becomes large, the function goes up, and as x becomes very negative, the function goes down. And so from that, we can determine the end behavior. In all of these cases, a negative sign right there on the lead coefficient would flip the graph upside down. So a negative sign right there would flip it over, or here might give us something like that, or a negative sign right there might give us something like that. But just by looking at the lead coefficient, or the power of the lead term and the sign, we can determine the end behavior. So with that in mind, we'll do 2 more examples, and we'll see that they are very quick and easy. In this one, we're given this function, and we're told to use limit notation to describe the end behavior. So all we want to do is talk about the limit as x approaches negative infinity. What is that? And the limit as x approaches positive infinity. That's what we're trying to ask, or what we're trying to find. And in this case, we have negative 7x to the 5th. We can ignore all the other terms. As x becomes really large or really small, this term will dominate all the others. And I notice that's an x to the 5th. So in my mind, I think this. A 5th power function looks something like that, but there's this negative sign right there. Don't forget about that. That's going to flip it over. So it's going to end up looking something like this. And there you have it. In the negative direction, this thing's going up. So this is positive infinity. And in the positive direction, this thing is zooming down. So in the positive direction here, it's negative infinity. And we can get that entirely by looking at the power and the sign of the lead term. And one more example, we have a 12th degree polynomial on top and an 8th degree polynomial on the bottom, and we're told to use limit notation to describe the end behavior. So we can ignore all the lower power terms in the numerator and in the denominator. And so we know that as x becomes large, f of x is going to approximately equal, or is going to behave something like this, negative 2x to the 12th over x to the 8th. And this will simplify, the x to the 12th over x to the 8th. That simplifies to negative 2x to the 4th. And that's easy. A fourth degree function looks something like this. But since there's a negative sign right there, that's going to flip it upside down. So it'll look something like that. And I have no idea exactly how it behaves in the middle here, but I do know that if there's a negative sign there and it's a fourth degree, then as x approaches negative infinity, this graph goes way down. And as it approaches positive infinity, it goes way down. So I can write that like this. The limit as x approaches negative infinity of f of x is negative infinity. And the limit as x approaches positive infinity is also negative infinity.